What is exactly concavity? I mean, we talked about concavity. We talked about concave up, happy, concave down, sad. But what actually is concavity? So here we go. The second derivative measures concavity, because what concavity is the change in the slope with respect to x. So our slope was the change in the y value with respect to x. So how does y change as x changes? Whereas concavity is how does the slope change as x changes? Concavity. Now, the thing with concavity, we're probably more interested in the sign of concavity rather than the number. Have a look at our standard parabola over there. On the very left-hand side, so as x is out at negative infinity, it has a slope which is negative something. And as we move from left to right, it's still going negative, 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 but it's becoming shallower and shallower and shallower. And then it becomes 0 at the turning point. And then it's getting positive, 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 positive. So it changes from negative to positive. So we say it has a positive change. It's increasing that change. And so that's all we really need to know. If it's positive, we'll end up with something that'll be concave up. It goes from a negative slope to a positive slope. And the reverse, therefore, would be negative. So let's formalise that. If our second derivative is greater than 0, we'll end up with a concave up curve, because we're going from something that's negative to something that's positive. So we're increasing the value of the slope. If the second derivative is less than 0, we end up with a curve that is concave down, because now we're decreasing the value of the slope as we go from left to right. And then we have this situation in between, and that's our inflection points that we talked about before. But you'll notice I've said possible point of inflection. We'll talk a bit more about that later. So okay, all I'm going to look at is the second derivative. So it's going to be a very rough sketch. I'm just going to look at the curve's concavity, and that'll give me an idea of the shape of the curve. Well, before I can find the second derivative, I've got to find the first derivative. There it is. 3x squared plus 10x plus 3. Differentiate a second time. 6x plus 10. Now I know it's going to be concave up when that second derivative is greater than 0. So if I solve that inequality, I know, okay, when x is greater than minus 5 on 3, the curve is concave up. Now logically, because all I've got to do is change the inequality sign, when it's less than minus 5 on 3, therefore it must be concave down. And straight away, I've got an idea of a picture. So I can draw a really rough picture. There's minus 5 on 3. I know on the right-hand side of 5 on 3, or minus 5 on 3, it'll be concave up. On the left-hand side, it'll be concave down. That's a very rough sketch. I haven't bothered to find out the location of those turning points or where the x-intercepts are or anything like that. Okay. But just say we want to identify, we want it a little bit more accurate. We're going to identify those turning points. If I can combine the first derivative information and the second derivative information, I can get a far more accurate picture. We know that all of those turning points are stationary points because the slope's horizontal. So the first thing we do is find the stationary points. And then we'll go and classify them. Now, we did that before with the first derivative by drawing up a table of values. But I don't actually need to do that now, because if I can combine it with the idea of concavity, I'll know what type of stationary point. Because if I'm concave up, and here's my stationary point, down the bottom here, it must be a minimum turning point. I couldn't have something that was concave down and be a minimum turning point, because if I'm concave down, I'll keep going down and down and down. There is no minimum. So I'm up here at the top now. I'd be a maximum. So combining the idea of finding the stationary points and then saying, all right, well, I know it's a stationary point, but it's also concave up, therefore, minimum turning point. But if it's concave down, maximum turning point. Here I am up at the top. And you can do that in the exam if you like. You can get your arms and wiggle your head. You go, I'm down the bottom. Or, oh, look, I'm at the top. So we're going to find the turning points of this particular cubic. We'll need the first derivative so we can locate the possibilities. and they're the second derivative, so I can go and classify them. So we solved the first derivative equals 0. That'll locate the possible stationary points, all of our stationary points. And that one, I hope, factorizes nicely. Yes, it does. 3x minus 1, x plus 1. So there are my two possibilities. So when x is equal to negative 1, if I substitute that into the second derivative, I get negative 4. Well, that's less than 0. Less than 0, concave down. Here I am up the top. So therefore, minus 1, and I worked out the y value was 2, is a maximum turning point. When I use a third, I actually get positive 4. And that one's greater than 0. Greater than 0, here I am down the bottom. Minimum turning point. So that's how we can identify those stationary points and what they are very quickly. I didn't have to draw that table of values. Now, that's not to say that the table of values is a bad idea, because if the second derivative was difficult to find, it might be quicker to just test either side of the first derivative. So I think it's important we have both ways of doing it, and then we just make our own decision. Well, if the second derivative is easy to find, I'll go and do that, and I'll use that. If it's difficult, I'll just use the first derivative and see what's happening there. Now let's talk a bit more about inflection points. So where it changes concavity, that's our inflection point. So that's another way of thinking about an inflection point. Right? When I described it before, inflection, I said, it's the opposite of reflection, and we get that twist. But have a look at the basic cubic over there at the twist. In fact, what is happening is it's changing its concavity. It was concave down and then changed to concave up. So that's actually what an inflection point is, where it changes concavity. How can we see if there's a change in concavity? Again, I can draw up my table of values, check either side of the point, and see where the concavity changes. So I'm going to find the inflection point, because there might be more than one, of this particular cubic. There's my derivative. There's my second derivative. Now when you're writing down, this is very important, it's possible points of inflection. Okay? It may not be a point of inflection. That's why we've then got to check either side. Okay? So it's possible points of inflection when the second derivative equals 0. And in this case, I only have one possibility, minus a half. So let's drop a table of values, but this time I'm going to be looking at the concavity of the curve. So minus a half, I know at minus a half there is no concavity at all. That's where it changes concavity. Pick a point on the left-hand side, pick a point on the right-hand side. So just like I did when we were working out maximum minimums using the first derivative. But now we're testing for inflection points. So on the left-hand side, can't go past any other possibility, but that's okay. There is no other possibility. So I chose negative 1 to test. At negative 1, negative 12 is our concavity. So it's changing quite quickly because the number's large, but it's concave down. We're changing from a negative slope to a positive slope. So sad. What's happening on the right-hand side? I'll use the point 0. Turns out to be positive 12. So yes, indeed, concavity has changed. Right? So yes, there is a change in concavity. Now it's important that you write that down, because just drawing up a table of values isn't really showing you know what a point of inflection is. So it's important you draw a conclusion from what you've done. And the conclusion is, yes, there is a change in concavity. So therefore, minus a half 3 is indeed a point of inflection. Horizontal point of inflection. That's one where it's a stationary point and it's a point of inflection as well. So the first derivative will equal 0. The second derivative will equal 0. And there will be a change in concavity. The third derivative will not equal what? Third derivative. Who started talking about the third derivative? The third derivative does not equal 0. I'm going to let you in on a little secret here. An alternative way of finding inflection points. Still got to find your possibilities. Okay? But just like when we went from the first derivative to the second derivative, before I knew about the second derivative, I drew a table of values and tested either side. And then we said, but hang on, I can use the second derivative to measure the change in the first derivative. Well, I can do the same thing here. Because remember, we're trying to find when does concavity change. Now, what measures change? The derivative. So I want to know if the second derivative is changing. Therefore, I use the third derivative. So my possible inflection points, finds them. Here's the actual rule. Okay. If when you're doing it, the first non-zero derivative is of odd order, third derivative, fifth derivative, seventh derivative, ninth derivative, or so on, then it is a point of inflection. So when you substitute in the actual point, if the first time you get an answer that is not zero happens to be on an odd derivative, it's a point of inflection. If it's of even order, it won't be a point of inflection. And so going back to the second derivative, remember we found second derivative is equal to zero. That was a possible point of inflection. It might not be. Because if the first time you substitute in the answer's not zero and it turns to be an even derivative, then it's not a point of inflection. Now, the vast majority of the ones that we look at, the third derivative will be the first time it happens. Very rare do we go past that one. So let's have a look at how I would have done that last question. I would have now found the third derivative, which is 24. Remember, we went and found our possible inflection point was at minus a half. Well, at minus a half, the third derivative is 24. Well, that's not equal to zero. Therefore, some change exists. Because we're saying we're measuring change with the third derivative. We've come up with a value. There is a change in the second derivative. So it must be a point of inflection. If the third derivative was equal to zero, what are we saying? We're saying there's no change in the second derivative. So it's not a point of inflection. So yes, therefore, there is a change in concavity. Again, important you write a conclusion to what you've just found out. So yeah, minus a half 3 is a point of inflection. Now let me give you a word of warning about this method. A lot of people are very uncomfortable about it because it's not in our textbooks, and so people think it's some sort of magic maths. Okay? Have a look at y equals x cubed over there. Y equals x cubed. We certainly know there's an inflection point at 0. We can see it. Okay? First derivative, 3x squared. Second derivative, 6x. Third derivative, 6. We're substituting in x equals 0. The first time that that derivative is not 0 is the third derivative. Thus, it's a point of inflection. Okay. Imagine if I'd drawn y equals x to the power of 4. Right? Just basically it's got that U shape. So, first derivative, 4x cubed. Second derivative, 12x squared. Third derivative, 24x. I'll go to the fourth derivative of 24. Some people put 4 primes. I like to use Roman numerals, but anyway, for the fourth derivative. Okay, the first time when I substitute in x equals 0, that I don't get 0 as an answer is the fourth derivative, which was an even one. So it's not a point of inflection. Oh good, that confirms what we were doing. Power of 5, 5x to the 4, 20x cubed, 60x squared, 120x, and 120. Now here's why people don't like using it. Because they think what the rule is that the third derivative must not equal 0. And if you use that rule here, at x equals 0, the third derivative is equal to 0. So you think, oh, our little rule breaks down, but that's not what our rule is. Our rule is the first time that it's not 0 is an odd one. If we keep going, the first time when we substitute in x equals 0, we don't get 0, is the fifth derivative. That's an odd number. So yes, it is a point of inflection. It holds true. It's similar to x to the power of 4 and turning points. Because what would we have said for turning points? To find the turning points, the first derivative would have to equal 0. Subbing x equals 0, yes, it's equal to 0. It's a turning point. But then I'd use my second derivative to classify it. Put in the second derivative, what do we get? 0. Oh, that means it hasn't got any concavity. Again, because the rule is wrong. Well, we teach you that it's the second derivative that you need to look at for the sign. And I guess because all of the cases we look at in high school maths, yeah, that works. But the reality is, no, what the actual rule is the first time it's not 0 is what you look at. The first time this one is not equal to 0 is the fourth derivative, which is an even derivative. So we know that it's a turning point and it's positive, so therefore it's concave up. But so we don't really need to worry about ones like that because the sorts of questions, certainly in TUNIT, that they're going to give us are going to be simple ones that work out quite nicely. But if you are going to be using the third derivative, make sure you explain yourself because the person marking it might go, what they're on about here, there's a load of rubbish. Okay, so explain yourself that, the first time it's not equal to 0 is an odd one. Dang, it is a point of inflection. Or if you prefer to just not worry about all that hassle, remember you can always just go back to drawing up a table of values and checking either side of the second derivative. Okay, 10E, we get to play with concavity. That rhymes, 10E, concavity.